Flipped classroom video for Maths A2 Unit 3, proof of chain, product and quotient rules. So, why? Why do we need to do this? Well, first of all, you will know this already, but maths is unique in that it can, in principle, be constructed using only certain basic or original assumptions known as axioms, and logical reasoning, including rules of inference. So, mathematical truth is different from other truths. And although the most useful aspect of the rules in this video is in the applying of them to differentiating complicated functions, the proofs themselves will deepen your understanding. So it is well worth working through them and understanding them. Understanding calculus in terms of limits will also reinforce your understanding of differentiation from first principles. And you probably recognise that diagram on the right, where when we move the blue point down the curve, eventually we get the tangent, and that gives us our delta y over delta x, which in the limit becomes dy by dx. You may remember that from AS. But reinforcing it will give you a firmer foundation for more differentiation from first principles, which will be coming up, and that's in your A2 studies and will perhaps help later on as well. So, having a look at the proof of the chain rule. First of all, we set it up so we let y equal f of g of x and we let u equals g of x. So that means that y is equal to f of u. And from that we get dy by du is equal to f dashed of u. So although u is set up as a function, we're now seeing it as a variable. And we can differentiate u because du by dx is just going to be g dashed of x. Now, if you remember back to differentiation from first principles, you'll remember about using deltas. So if delta x is a small change in x, and delta y and delta u are small changes in y and u, then we can say that delta y over delta x is equal to delta y over delta u times delta u over delta x. And that is simply algebra, because at the moment the deltas are all numbers, so delta y is a number, delta x is a number, and so we can treat them algebraically. Now, as delta x tends to naught, you also will probably remember that that then allows us to say that dy by dx is equal to the limit, as delta x tends to naught, of delta y over delta x. And in this case, because we've now set up delta y over delta x to be equal to delta y over delta u times delta u over delta x, we now have that dy by dx is equal to the limit as delta x tends to naught of delta y over delta u times delta u over delta x. Now in this case, as delta x tends to naught, delta u will also tend to naught because they're connected. And so we can say that the limit of delta u tending to naught of delta y over delta u times the limit of delta x tending to naught of delta u divided by delta x is equal to the line above. Now I should point out that technically what we're assuming here is that the product of the limits, so the limit of one times the limit of the other, is equal to the limit of the products, which is the line above. This is true in all of the situations that we're going to deal with in A-level. It's a very technical matter that you might look at later on if you study maths further. But it's an acceptable move at this point. Okay, so what is the limit of delta u tending to naught of delta y over delta u? Well, that is dy by du. And the limit of delta x tending to naught of delta u over delta x is du by dx. But we already know that dy by du is f dashed of u, and du by dx is g dashed of x. And furthermore, we know that u is equal to g of x, and so we now have that being equal to f dashed of g of x times g dashed of x. And notice that whole chain of equals started with dy by dx equals. So if y is equal to f of g of x, then dy by dx is equal to f dashed of g of x times g dashed of x, which is the chain rule that you've seen previously. Okay, so after all that, we'll move on to the proof of the product rule. And this time we're going to let u be the function f of x and v be the function g of x. And so that means that if we do the product f of x times g of x and make that equal to y, that also means that y is equal to u times v. So again, we're looking at small changes. So if delta x is a small change in x, and delta y, delta u, and delta v are small changes in y, u, and v, then first of all we can say that y plus delta y must be u plus delta u times v plus delta v, because y equals u times v. We can also then subtract y from both sides. Now on the left hand side we subtract y, which leaves us with delta y. On the right hand side, when we subtract y, we recognise that y is equal to uv, so we subtract uv, but we've still just subtracted the same thing from both sides. Then if we were to open that bracket, we'd get four terms, which would be uv, u delta v, delta u times v, and delta u times delta v. But the first of those terms, which is uv, we've got to take away uv there, so what we're left with is the u delta v plus v delta u plus delta u delta v. And now we divide everything through by delta x, which leaves us with, on the left hand side we had delta y, so now we have delta y divided by delta x. And then for each of those three terms we use the deltas to make fractions, so u delta v becomes u delta v divided by delta x, v delta u becomes v delta u divided by delta x, and delta u delta v becomes delta u delta v divided by delta x. So when delta x tends to 0, delta y by delta x becomes du by dx, delta u divided by delta x becomes du by dx, delta v divided by delta x becomes dv by dx, delta u delta v divided by delta x tends to 0, and that is because the delta u and the delta v are approaching 0 at the same time as the delta x is, and because they're multiplying, when you multiply very small things together they get very, very, very small, so that's why that will tend to 0. Now we know that dy by dx is the limit as delta x tends to 0 of delta y over delta x, which we learnt in AS level when we were doing differentiation from first principles. And thinking of the bottom line on the opposite column, that tells us that that is equal to the limit as delta x tends to 0 of the right hand side of that, which is our u delta v over delta x plus v delta u over delta x plus delta u delta v over delta x. And we can split those up. So if we look above, we have those delta u delta x tending to du by dx, and what that means is the limit as delta u over delta x tends and what that means is the limit as delta x tends to 0 of delta u over delta x is du by dx. So that means that when we do the limit as delta x tends to 0 of u delta v over delta x, that's going to give us u times dv by dx, because the u is unaffected by the fact that we're taking a limit. The second term, the delta u divided by delta x is going to become du by dx, leaving us with v du by dx, and the limit of the third term, as we can see above, is going to be 0 because it's tending to 0. And so finally we can say, instead of dy by dx, because y is uv, we can say that if we do d by dx, or differentiate uv, then that will give us u dv by dx plus v du by dx, or in fast terms, u dv dx plus v du dx. Okay, so proof of the quotient rule. So we have u being f of x and v being g of x as before, and so y equals f of x over g of x is the same as saying y equals u over v. And what we can say about that is, of course, that that means it's equal to u times v to the power of minus 1. Okay, we are now going to use the product rule because we have y expressed as a product, so it's going to be u times the v to the minus 1 differentiated plus v to the minus 1 times u differentiated. The chain rule tells us that if we differentiate v to the minus 1, we get minus v to the minus 2 times dv by dx. And that might look a bit weird, but remember that v is a function, as we saw at the top. V is equal to g of x, and so that means that v to the power of minus 1 is a function of a function. So the inner function is v, so that gives us our dv by dx. The outer function is to the minus 1, and if we differentiate to the minus 1, we get a minus 1 coming down, or just minus. We subtract 1 from the power, which gives us our minus 2, and we pop the function back in, hence minus v to the minus 2. Okay, also note here that we're using the chain rule and the product rule to prove the quotient rule. And this is a good example of how mathematics is built up on proof. We prove things and then we can use them to prove other things. Okay, so having done the product rule and the chain rule, we can now say that dy by dx is equal to, well, we have that line above, u d by dx of v to the minus 1. We can replace that by minus u v to the minus 2 dv by dx by using what we've just done with the chain rule, plus what we had before, which is v to the minus 1 du by dx. If we swap those terms round, we get that dy by dx is v to the minus 1 times du by dx, take away u v to the minus 2 times dv by dx. Then we can convert v to the minus 1 into v divided by v squared. U times v to the minus 2 is, of course, u over v squared, and so we get this expression, dy by dx is equal to v over v squared times du by dx, take away u over v squared times dv by dx. And that means we've got v squared on the bottom of both of the fractions, which gives us dy by dx is equal to v du dx minus u dv dx over v squared. So finally we can write that as d by dx of the quotient u over v gives us v du dx minus u dv dx over v squared.